Mhm.
Hello, and welcome to our senior design presentation. We are the Resistor Rangers, and today we're excited to share our project. To start, we'll introduce the team. I'm Doug Harrison.
I'm Mitchell Woolhoff.
I'm Bianca Lemon.
Oh,
And I'm Stephen Evans.
there he is.
Mhm. Yeah.
Can I get the next slide? So power outages can be detrimental to research efforts. So we chose a project to create an uninterrupted power system for a new research center at ASU that'll help students, faculty, and other researchers. The hypothetical building, already has a backup generator and a solar array, but these alone can't ensure continuous operation. So we needed to design a battery bank for power storage and a microgrid that will incorporate system protection, island protection, load shedding, and synchronization back to the utility feed for seamless automation. The project here focuses on designing the microgrid system that can maintain power to a critical research environment. The primary parts is the battery bank that we designed to deliver 30 kilowatts for 5 minutes of uninterrupted power, to include a 100 kilowatt rooftop solar array to reduce loading on the utility grid, and a 150 kilowatt generator, diesel powered generator, to maintain long term power during an extended outage. The system also has automated load shedding for 10 feeder breakers to make sure that the critical loads are prioritized, and real time automation for seamless transitions between power sources. The 100 kilowatt rooftop PV array takes the energy from the sun, converts it to electricity, and the actual output that we expect to see is somewhere between 75 and 85 kilowatts. That's due to a variety of factors, mostly weather, though. So this will allow us to reduce overall energy demand on the grid, reducing our dependency, reducing our operating costs. And it also works with the automation to supplement the generator output to allow more loads to be powered during a long-term outage. Well, at least as long as the sun's shining.
PSCAD is a software tool used for simulating electromagnetic transients in power systems. It's what we decided to use for a simulation of the microgrid system. Typically, engineers rely on it to model electrical networks, control systems, and power equipment like transformers. One of its strongest features is its ability to provide detailed time domain simulations, capturing fast transient effects such as switching events, fault responses, and harmonic distortions, making it particularly useful for grid stability studies and renewable energy integration. PSCAD also features a user-friendly graphical interface, allowing users like ourselves to easily build circuit models, connect system components, and adjust parameters in real time. This feature has been invaluable to us as we progress through our project, as it's allowed us to pinpoint issues that arise as we've tried to simulate the microgrid system. Additionally, easy plotting of various system parameters has allowed us to confirm correct system behavior and values. One of the difficulties in simulating microgrid systems in PSCAD is the complexity of coordinating multiple energy sources. Unlike a traditional power grid, which has large centralized generators supplying power, microgrids rely on a mix of sources like diesel generators, solar panels, and batteries. Simulating how these elements interact in PSCAD requires precise tuning of system parameters, control strategies, and load sharing mechanisms. Additionally, we've only been functioning on the free version of PSCAD, which has limited us to 15 nodes. So we've departmentalized the project into smaller bits, allowing us to work on sub-projects that we then integrate together into a master model. Moving forward into the technical side of the diesel generator, synchronous generators are essential for microgrid operation. They provide reliable power source in a decentralized system such as a microgrid. A generator's rotor is driven by a prime mover, such as a diesel engine or a sub-turbine, which creates a rotating magnetic field that induces alternating current in the stator windings. Unlike large power plants that benefit from the stability and inertia provided by multiple interconnected generators, microgrids often rely on one or a few generators to maintain voltage and frequency. As a result, each generator must operate within very tight tolerances. with its rotor speed precisely matching the system's required synchronous speed. Load fluctuations in a microgrid can be significant, especially when renewable energy sources, such as our PV array, have differentiating power supplies. Any deviation from these parameters can lead to voltage fluctuations and unstable power quality. In PSCAD, these generators are modeled using a combination of electrical and mechanical equations. The software simulates stator and rotor dynamics, magnetic field interactions, and mechanical inertia to replicate real-world behavior. There are some pre-configured models for synchronous generators, which we have utilized, parameterizing them to how the system would need fit. One of the key components of a synchronous generator simulation is the exciter, which I'll show on the next slide here. The exciter is responsible for regulating the field current supplied to the rotor, which in turn controls the terminal voltage of the generator. In PSCAD, exciters are implemented as control blocks that take voltage measurements from the generator's terminals and adjust the field voltage accordingly. Different exciter models exist, ranging from basic voltage regulators to more advanced feedback systems. Properly configuring an exciter ensures that the generator maintains a steady voltage output, even with fluctuating load conditions. Additionally, governors play a similar role in regulating the mechanical power input to the generator. However, they adjust the prime mover, in this case for the diesel engine, which controls the generator's speed and maintains frequency stability. In PSCAD, and in the case of a diesel generator, governors are modeled as dynamic control systems that respond to frequency deviations by increasing or decreasing the fuel input to the engine. This helps keep the generator running at the desired speed, ensuring that it stays synchronized with the system. Several critical control functions are required for proper operation and are part of the deliverables for a project. Voltage rise and lower controls, handled with the exciter, allow adjustments to the generator's terminal voltage to match system requirements. Similarly, speed raise and lower controls are handled in the governor, and they fine-tune the governor's operating frequency. Two important operational modes are ISO mode and droop mode. In ISO mode, the generator maintains a fixed frequency regardless of load changes, making it ideal for islanded microgrid operation, where the generator is the only source supplying the loads. Droop mode, on the other hand, allows the generator to adjust its frequency slightly in response to load variations, ensuring that multiple generators share the load without competing against each other. In real-world synchronous generators, these operational modes and controls are typically built-in functions. However, PSCAD synchronous machines lack these features, meaning configuration of these modes correctly in PSCAD is essential for achieving realistic, simple system behavior. Despite the capabilities of PSCAD, however, we have encountered several challenges in simulating diesel generators specifically. While PSCAD has multiple built-in generator models and governor models, none of them are parameterized specifically to control a diesel engine. Diesel generator models require detailed prime mover characteristics, such as fuel consumption curves, which are not always well documented. Additionally, PSCAD synchronous machine models come with limited and sometimes unclear documentation, making it difficult to understand their internal workings. One of the biggest hurdles has been implementing ISO and droop modes correctly with the simulation.
Again, my name is Bianca Lemon, and I will be discussing the networking technical of our microgrid system controller. Our microgrid system controller mainly focuses on protection, automation, and communication architecture using cell equipment. On this slide right here, the microgrid layer architecture is designed for modularity, scalability, and clarity in operation and control. Our microgrid follows a 4-layer architecture. Layer 0 in the image includes physical power devices like circuit breakers, CTVTs, and power generation controllers. This is considered the foundation of our microgrid system. These devices don't communicate. They act based on inputs or direct control from the higher layers. Layer 1 includes protective relays, remote IOs, and metering systems. Intelligent electronic devices are the bridge between raw electrical data and the control system. They take real-time measurements, make decisions based on pre-programmed logic, and send data upstream. Layer 2 in this architecture is where the communication network lives, including gateways and switches. This layer ensures seamless data flow and time synchronization. And it also ensures secure control commands across the system. Layer 3 is central control, where our microgrid controller runs automation logic. It's here that all of the protection and automation rules are processed, often in real time, to keep the system safe and efficient. And in layer 4, hosts higher level software for visualization optimization, often interfacing with outside networks that may be used, depending on the customer. This layer can also link to utility control centers, cloud platforms, supporting functions like demand response or market participation. This layered approach that we use separates power hardware from communication and logic. It also helps enhance reliability and scalability for our system. Next slide, please. We're utilizing the cell communication architecture network set up for our design. So in the slide, it shows an example of the networking system from the hardware that they're using. We're using Cell 3530 real-time automation controllers as central nodes. These interface with relays like the Cell 751 for feeder protection and the Cell 735 for power communications, are handled over the DMP Ethernet with coaxial and fiber cables. Each line type is mapped out in this diagram. The Cell 2730M is the managed Ethernet switch aggregating data, while the Cell 2407 GPS clock ensures precise time synchronization in our system. All field devices are connected to the automation control through fiber optic network for speed and electromagnetic interference immunity. In this microgrid controller is programmed to manage key protections and automation tasks. For instance, island detection. That is when the utility grid fails or goes out of tolerance. The controller detects this through frequency and voltage sensing relays, signaling the microgrid to enter island mode. Secondly, isolation from utility. Using this automated breaker and control logic, the microgrid electrically separates itself from the main utility grid to avoid backfeeding and ensure personal safety. Thirdly, generator and solar startup and synchronization. Once isolated, the controller initiates a smooth startup and backup generation. Synchronization logic based on phase, voltage, frequency matching is executed to connect sources like solar and diesel gensets safely in our system. Next, load shedding. If generation can't meet demand, non-essential feeders are shed using the Cell 751 relays based on priority tags. This avoids brownouts and total collapse and maintains stability for critical loads. Restoration and synchronization to utility. When a utility source returns, the system monitors it for stability. Once verified, the controller performs a closed transition resynchronization to grid standards and reconnects loads and phases. So in summary, this network microgrid with solar and backup generation relies well-coordinated protection and automation strategies managed through cell architecture. These layer ensures fast islanding, safe isolation, controlled restoration, and flexible load management, all crucial for resilient and sustainable power delivery.
Again, I am Stephen Evans. The UPS in our microgrid system is a critical component designed for simplicity and reliability. It is directly connected to the feeder powering the lab, and in the event of a power grid outage, it seamlessly provides 5 minutes of power supply. This ensures that our prioritized load continues to operate without interruption. The UPS achieves this by storing energy in a battery bank as DC voltage. When needed, it efficiently converts the stored DC voltage into AC voltage, delivering a stable power supply to keep essential operations running. One of our first tasks last semester was to determine the appropriate battery size required to sustain lab operations during a power outage. We conducted detailed calculations, incorporated a safety margin to account for unforeseen variables, and concluded that a 3 kilowatt-hour battery would be sufficient. We chose lithium-ion-based batteries due to their combination of high energy density, longevity, efficiency, and low maintenance requirements. We also noted that lithium-ion batteries can cause self-ionizing fires, meaning the facility will require special fire suppression and containment processes in order to operate. To validate our calculations and to provide a proof of concept for our design last semester, we developed a MATLAB simulation to model the core functionalities of our system, such as island detection, load shedding, synchronization, and battery backup operation. The script uses manually inputted system parameters and solar data from Tempe, Arizona, to define the behavior of components like the solar array, battery bank, generator, and load priorities. As the power source changes, the program compares the available power to the demand of each of the loads, skipping the loads that will not receive enough power to operate safely. The simulation was programmed to generate plots that illustrate the lab's operational timeline during power outages. As shown in the plot displayed on the top right corner, grid power is lost at the 5-minute mark. The battery system sustains lab operations for the next 5 minutes until the generator takes over at the 10-minute mark, maintaining operations seamlessly until the grid power is restored. Additionally, the simulation provides a detailed plot showcasing the battery's state of charge over time. Beyond these visual insights, the MATLAB program also dynamically displays which loads remain powered on based on the available power from all sources, ensuring a clear understanding of power distribution and prioritization.
This is Doug Harrison again. Some of the other work we completed last semester, we created a flow chart to indicate where our main focuses needed to be and the flow of information within the system. Being a microgrid system, the communications aspects can be a little more complex than just a typical single feeder to a facility. We also completed our logic diagram to kind of help us work through in a pseudocode fashion to set up our communications from one step to the next. Okay, the next slide, please. And so the little bit of work we have left, we're going to continue working on our PSCAD models. As was said before, our PSCAD simulations are proving to be a bit more challenging than the MATLAB simulations because of the nature of the software that we had found to use, and then the nature of the deliverables that were requested by us of SEL. So once we complete our models, we'll have to combine them all into one large master model and then simulate and test everything. We do believe.
Excuse me.
Yes.
Sorry to cut you through, but your fifth member is here, so if you guys can give him chance, like if it's his part and you don't know about that, I just let you know.
Eddie, you want to take this one? We're on slide 14, Eddie. No, we
No.
can't hear you, buddy. I guess he's having some technical difficulties.
Yeah.
So from our work from last semester, we should be between the work from last semester and what we have left for this semester, we should be in pretty good shape to accomplish all of our objectives on time and get everything tested and ready for demo day. So that is the state of our project so far. Like I said, I think we're in really good shape to meet all of our objectives and accomplish all of our deliverables for SEL. Thank you for listening to our presentation.
We're happy to take any questions as well.
Yeah. I think Tuyog will go first.
Cool. So the one question I had was what's like the practical application for this? Where in the industry, or like what kind of what's the use case for what you're doing here with the microgrid?
Well, specifically right now in the lab space, it's essentially assume that there's either equipment or studies that are happening in the lab that require uninterrupted power. So if there's any loss of power, possibly loss of data could occur or failure to equipment could occur. And so it's essential that the lab is continuously receiving power. Outside in the world, though, there's lots of other applications. For example, hospitals. Obviously, if there's people hooked up to machines with life-saving equipment, if you lose power, that can be detrimental.
Right.
Server spaces are also another great area for microgrids. Any place that you need uninterrupted power supply is a great place for a microgrid system to be implemented.
Gotcha.
These type of systems also work well in small communities, off-grid communities, island communities, literal island communities, and
Right.
anywhere where bulk power distribution isn't readily available.
I've also seen this system in the military as well for medical facilities on the go, which kept up like during COVID, they used the same system for the demand in larger medical facilities. So
Right. Gotcha. Oh, thanks.
Mhm. Yeah, I don't have any questions from my side. So
Yeah, I thought it
you
was a pretty
guys,
good presentation.
Mhm. um, just what about your fifth? Um,
Can you guys hear me now?
Hey, there he is.
yeah,
Hey,
yeah,
Eddie.
Okay.
we can
Yeah,
hear you.
sorry about that. I got rear-ended on my way from work today, so I'm just dealing with
No
that.
way.
Yeah, so sorry about that. I
That's
joined
all.
in on my phone now. So I had to talk to there, but my mic wasn't working either, so sorry about that.
Mm-hmm.
That's
No
awesome.
worries.
Everybody okay?
Okay.
Yeah, everything's fine. It's just physical stuff.
Man.
Mhm.
Sorry to hear that, man.
Yeah,
Yeah,
no, you're
that
good.
sucks, man.
Um, just
Yeah,
from
what?
yeah, so you're what do you want to do for him? Like he should get a chance. Like he came late, but he should get a chance for.
Not his fault he got rear-ended,
Yeah,
so
yeah, yeah.
Yeah.
It's not his fault, obviously.
I
Uh,
guess we can wait for the insurance report to find out whose fault it was and then grade him accordingly.
oh, wow.
That's right.
It's fine. Yeah,
Yeah.
that's a good one. No worries. Um, I would suggest that. Can you summarize the whole project for us? That should be a good
Yes.
place where we can grade you. Is it okay with you if it's like
Yeah, we can go ahead and do that. What
Can't hear you
exactly?
again very
What was
well.
that? Oh shoot.
You
Yeah, there you
sound
go.
better now.
It's
yeah,
good.
yeah, no, yeah.
Oh, okay. Yeah, I don't think I was on the entirely on the mic. Yeah. So, basically, right now, the what I was mainly working on is the PV technical overview. So that's pretty much we're focused on using the PV array in case that's like our last resort. I mean, I had my whole like script written out that I was going to summarize on that, but it's basically a 100 kilowatt rooftop PV array that we're trying to go for here. Um, but as far as the work, we're kind of straight away from what I was gonna do, and we're changing ideas. So I need to work with Mitchell now on what how we're gonna approach it. But I mean, as far as right now, we're all kind of working on our separate sections, and I believe they're still all in separate models, and then eventually we're gonna have to work into integrating everything to work seamlessly together, which would be the
What's
battery system, the PV array, the backup generator, stuff like that.
what's about your part? Can you explain a bit about your part? What you do?
Yeah, so I was working in PS CAD. I was basically trying to create an exponential model that would show the how it would basically go from 100 kilowatts and discharge like over time. Um, but we kind of strayed away from that now, so I'm gonna be working with Mitchell now on the preview array. Hopefully Bianca as well. Um, but yeah, so what I was working on is gonna change now moving forward.
Mhm. Okay.
Could you tell me why it changed again? I'm sorry if you covered it during the
Yeah.
presentation.
Well, one, I couldn't run what I was trying to run with just the normal free trial. So I had to
Yeah.
acquire one of the student licenses for PSCAD, and we weren't able to model exactly what we are trying to do. So instead of spending more time on that, we decided to just move forward with other things.
Makes sense.
Gotcha. If you got the PSCAD subscription or the license,
hmm
would you be able to do what you originally intended? I'm
yeah,
just
I
curious.
wanted.
There's nothing like I'm just curious.
Right, yeah, I wanted to still give it a try for a bit, but that would be more like kind of on my own time because I've had some free time even like during work. But I was thinking when I wasn't working with Mitchell or Bianca on what we initially want or what we're gonna go after now, I was still gonna try to make that model just so because I feel like it would be a good way to show how the solar system would be discharged.
Got
Okay.
you. Yeah, cool.
So,
And did
cool.
you and just because I know Mitchell sent me the email. Did you guys hear back about the licensing at all from Talia or anybody or no? Not yet.
Yes. So I think Doug is already on that.
Yep.
I think everybody else is trying to get on that. But I finally got a response yesterday and I was able to get I haven't actually set it up yet, but they did send me a license over, so I'll be working on that tomorrow morning.
And just to clarify quickly, what he's referring to is PSCAD offered us temporary 1 month student licenses for free.
Okay.
And in terms of getting the 6 month license, the professor emailed back and said that the form I provided was sufficient. So we're just waiting to hear back from Talia, essentially.
Okay. Cool.
But we
Okay.
have
1
those.
month
We have
sounds
those
good.
1 month. We have those 1 month licenses. I think Eddie. I know Bianca's also might have gotten one. Doug has one.
Yep.
We're kind of staggering ourselves so that we have coverage with the full license. We do have a very rough draft of the microgrid system in PSCAD, but it needs tuning up in the PV array so that it works, so that it behaves correctly with the other sources. And then we'll be able to go into testing and simulation to see how it behaves with different shedding and different system behaviors and such.
Yeah,
Right.
the majority of it's completed. The trick now is to make it do all the things that it wasn't necessarily initially intended for, like controlling a diesel generator. Apparently, it wasn't meant for that. It's PSCAD is owned by a hydroelectric company, so most of their simulations are based on hydroelectric grids.
Oh, got you.
So a
Like
lot
all
of the
their
stuff,
governor
like
models and such.
right, the diesel
Gotcha.
generator governor, we're having to model from scratch, which is exciting and fun.
Got you. Okay. So is your final product during the demo day going to be the PSCAD model of microgrid?
The simulation, yeah. We'll
Okay.
be able to run it, adjust, drop out the utility, watch the transition, adjust solar output, things like that. It should be rather comprehensive.
Cool. Awesome. All
Any
right.
other questions for us?
No,
I think
I'm good.
we have
Thank you.
everything. Thank
It
you
was
so
a good
much.
presentation. Thank you, guys.
Yeah,
Thank
really
you.
good
Thank you guys
presentation,
for
guys.
your understanding.
Yeah, thank you so much. And we're glad you're feeling okay, Eddie. I'm
Yeah,
glad we
thanks,
found out
guys.
where you were at. Yeah.
We were all worried about you.
Sorry about
Studio,
that.
can you stay back for a
Yeah,
moment,
for
5 minutes? Yeah. Okay.
Okay.
But
You guys can leave. Yeah.
I'll email you a Zoom link. Just join my Zoom.
Yeah, sure. Works. Cool.
Cool.
Okay.
Thank
And
you.
All right.
with the recording, am I meant to send this to somebody?
Yeah,
To both of
to both of them, yeah.
Okay.
Yeah.
I'll get those sent over. Thank you.
Yeah. Thank you.